In the previous lecture, we have discussed in very detail the calculation of binding energy and Madelung constant of ionic crystals. Now today we are going to see the problem of ionic crystal again, but in this lecture our aim is to calculate the repulsive exponent in case of ionic crystal. When you say a repulsive exponent, what does it mean? You know, in case of ionic crystal, there are two types of interactions: attractive interaction and repulsive interaction. Coulombian interaction and the repulsive interaction. Coulombian interaction may be attractive or repulsive, but when the two ions of an ionic crystal comes closer and closer, and the electronic clouds of the two ions get overlapped, then you know a repulsive force acts between the ions. That is called repulsive interaction. And you have seen in the previous lecture that that repulsive force, due to that repulsive force, a repulsive energy is produced, and that repulsive energy is given by Bn divided by R to the power n, where Bn is repulsive constant and R is the separation between the two ions, and n is an exponent, a number on R. Actually, in this lecture, our aim is to find the value of this n. What will be the value of n in this case of ionic crystal? Our aim is to find this. Actually, this repulsive exponent is found in terms of the adiabatic compressibility of the crystal, or you can also say that adiabatic bulk modulus of the crystal. We can obtain the value of this repulsive exponent. Okay, so let us see how we can find this repulsive exponent. I have told you in the previous lecture that n is a very large number. In Coulombian force, you know the force obeys the inverse square law, that is, it varies with r to the power minus 2. Okay, 1 over r square. But in this case, you will see that this n is very large in comparison to 2. It is almost equal to 8. But how we can express this repulsive exponent in terms of the adiabatic compressibility of ionic crystal? Our aim is to discuss in this lecture. Okay. So we will start to calculate it from the basic definition of the bulk modulus of elasticity of the material, or the adiabatic compressibility of the material. You know, the adiabatic bulk modulus. When you say adiabatic bulk modulus, it means our system is not exchanging heat energy with its surroundings. In that condition, the general definition of bulk modulus of elasticity B is what? This is simply bulk stress by bulk strain. And you know, the change in pressure dP, this is the measure of bulk stress. dP, which is change in pressure, that is called bulk stress or volume stress. Okay, and volume strain, that will be equal to simply change in volume dV over original volume V. So this B is defined as dP over dV by V. Actually, dP is the measure of bulk stress, and this dV by V is the measure of bulk strain. But here we have substituted a negative sign. Why this negative sign is used? Because you know, whenever pressure will increase, volume will decrease. So when dP is positive, then definitely this dV will be negative, and the modulus of elasticity must be positive. So to avoid the negative sign in definition, we always use minus sign. So the bulk modulus of elasticity of any material, this is general definition. This is denoted by the symbol B and it is defined by minus dP over dV by V. Okay, and equivalently you may write it as this is equal to minus V times dP by dV. Okay, and as you know, the adiabatic compressibility is simply the reciprocal of bulk modulus of elasticity. So if K is the adiabatic compressibility, then 1 over K, that is reciprocal of K, that will be equal to B. And so you can say that 1 over K is equal to minus V times dP by dV. Okay? Or if your aim is to express K, you can express it like it. This K is equal to minus 1 over V times dV by dP. Okay? And as I have told you that this dP is the small change in pressure required to produce the volumetric strain dV by V, or this dP is also the measure of volume stress. Okay, change in pressure is the measure of volume stress. Okay. Now we consider that our system, that is our crystal, is suffering adiabatic compression. It means you apply a compressive force on the specimen, just like this. As you can see in this figure, the system, that is our crystal, is compressed. Okay, and this compression is adiabatic. When you say that we compress the system adiabatically or the system suffers adiabatic compression, what does it mean? It means there is no exchange of energy between this system and its surrounding. Okay, so we can find the value of this derivative dP by dV or dV by dP in terms of the first law of thermodynamics. You know, first law of thermodynamics reads as del Q equal to d phi plus P dV. P dV is actually the elementary work done and d phi is change in energy. Okay, and del Q is the heat given to the system or heat released by the system. But as the process is adiabatic, so we know this del Q will be equal to 0. So in this present condition, when we consider adiabatic compression, we must take this del Q equal to 0. Okay, and therefore you can say that when del Q will be 0, then we have, according to first law of thermodynamics, 0 equal to d phi plus P dV. And if d phi plus P dV is 0, then what will be d phi? D phi is equal to minus P dV. Okay, and so that P is equal to minus d phi by dV. And so you can, if you will differentiate this P with respect to volume V, what will be your result? Then dP by dV, as you know P, and if your aim is to find dP by dV, this dP by dV, this will be equal to what? This will be minus d2 phi by dV square. Okay, minus d2 phi by dV square. But you can see this equation 1a or 1b. Actually in equation 1 we have defined B, and in equation 1b we have defined K, which is just the reciprocal of B. So in these two equations you can see in first equation 1a the factor dP by dV is present, and in 1b the factor dV by dP is present. And here we have calculated the value of dP by dV. Okay, and so let us substitute this value of dP by dV in that equation. So when we will substitute this value, what will be our result? You can see B is equal to 1 over K, and so this 1 over K will be equal to V times d2 phi by dV square, d2 phi by dV square. Okay, so when we have used equation 2 in 1, we have got this result. Okay, B equal to this much. Okay, now we will express this d phi by dV in terms of the interatomic separation, because you know the potential energy or the energy of interaction actually depends on the separation between the two ions R. Okay, so first of all we will express phi as a function of R. Okay, here if in our equation the term is d2 phi by dv square, but our aim is to express this d2 phi this phi as a function of R, then let us think about function of function. Okay, function of a function. So taking the concept of function of a function under account, we can find d phi by dv may be written as d phi by dr times dr by dv. Okay, you can write it. And if you will find the second order derivative d2 phi by dv square, how we can find it? You can see this will be, this d2 phi by dv square will be simply d dv d phi by dv. Okay, but d phi by dv you have written here, you can see this is actually d phi by dr times dr by dv. So I have substituted here this factor instead of d phi by dv. Okay, now see inside this bracket there is a product of two functions. The first one is d phi by dr and the second one is dr by dv. So following the rules of differentiation of product of two functions, you can see what will be the simplification. Actually when this operator d dv will be operated on the second factor dr by dv, then our result will be d phi by dr times d2r by dv square. Okay, and plus now we will operate this d dv on d phi by dr and take this dr by dv at each. So dr by dv has been taken at each and operator d dv has been operated on d phi by dr. You can see the first term is at each. You can see this is d phi by dr times d2r by dv square and plus dr by dv. Now this d dv d phi by dr, we can again think about function of function, and so this can be written as d dr d phi by dr times dr by dv. You can see if this dr here and this dr here will cancel out, the result will remain same. Okay, and so finally we get that this d2v by dv square equal to d phi by dr times d2r by dv square plus. Now here you can see in the second term this dr by dv times dr by dv. So this will be equal to dr by dv whole square, and d dr d phi by dr, this is equal to d2 phi by dr square. Okay, so finally we have obtained the value of the second order derivative of phi with respect to v, where phi actually represents the binding energy or the not binding energy but interaction energy. This will be binding energy when R will be equal to R naught. Okay, now we know that when crystal is formed in equilibrium, then the equilibrium separation is denoted by R naught, and when the system is in equilibrium, phi is at its minimum value, and so this d phi by dr is equal to 0. Okay, so if you talk about the equilibrium condition, then as d phi by dr will be 0 in equilibrium condition, so you can see the RHS of this equation 4. the first term will vanish because the first term in RHS of equation 4 contains d phi by dr. But in equilibrium state, this d phi by dr is 0. And so, when that term will vanish, our result in equation 4 will be what? This will be simply d2 phi by dv square equal to dr by dv whole square times d2 phi by dr square. Okay? But this result is in case of equilibrium state, and you know when the system is in equilibrium, then R is equal to R naught. So you must write here the condition that for R equal to R naught. It means when R will be equal to R naught, only then you can say that this d2 phi by dv square is equal to this much. Okay? Now we have obtained the value of this d2 phi by dv square in equilibrium condition. So after getting the value of d2 phi by dv square in equilibrium state, by the use of this equation 3, now you can obtain the value of bulk modulus or the adiabatic compressibility K of your crystal. Okay? And for this, you have to substitute the value of this d2 phi by dv square, which we have obtained just now in this equation. So let us see. If your aim is to find b or 1 over k, you must multiply this d2 pi by dv square with v. Okay, with v. So let us see here. So b is equal to 1 over k, and that will be equal to v times this much, d2 pi by dv square. But we have seen that d2 pi by dv square is equal to this much. This is dr by dv whole square times d2 pi by dv, d2 pi by dr square. Okay. So I have substituted it here, and after substituting, we see that b, which is equal to 1 over k, that equals v times d2 pi by dr square times dr by dv whole square at r equal to r naught. Okay. This is actually the general result which we have obtained for the adiabatic compressibility K or the bulk modulus B of the crystal. But now we are going to see the particular case of ionic crystal. Till now we have never considered a particular ionic crystal, but as I have told you in the beginning of my lecture, that our aim is to find the repulsive exponent of ionic crystal. But the results obtained up to equation 5 is valid for all crystals, all solids. But now we are going to apply this result specifically for the ionic crystals. You know, NaCl is a very good example, a very important example of ionic crystal. Okay, so taking the example of NaCl, now our further calculation will be made. You know, you have studied earlier while in the study of the crystal structure, which I have provided in my playlist in very detail, that in NaCl structure, the lattice parameter A is equal to 2R. You can remember it. We have already studied these things in our previous lectures on crystal structure. And if the unit cell of NaCl consists of 4 molecules, that is 4 Na plus ion and 4 Cl minus ion, then the volume of the unit cell of NaCl crystal is 8R cube. You can remember it, okay? Because you have already learned these things in your previous lectures, okay? So mark it. If there are 4 molecules, how many molecules? 4 molecules in the unit cell of an NaCl crystal, then the volume of the unit cell is 8R cube. Okay, so can you say what will be the volume of one molecule of the NaCl crystal? Since volume of 4 molecules is 8R cube, so volume of one molecule will be simply 1 over 4 times 8R cube. Okay, so you can say that the volume occupied per molecule of NaCl is equal to this much. This is 1 over 4 times 8R cube. Okay, and that will be equal to 2R cube. So this 2R cube is the volume of each molecule of the NaCl crystal. Okay. Now let us consider that in the specimen of our NaCl crystal there are n molecules of NaCl. N is the total number of molecules in our specimen. As you have learned that volume of one molecule of NaCl is 2R cube. So the volume of n molecules will be what? That will be simply n times volume of each molecule, and volume of each molecule is 2R cube. So volume V, this will be equal to n times 2R cube. Okay, and you can write it that V is equal to 2n times R cube. Okay, 2n times R cube. Now here I have expressed the volume of the crystal as a function of R, and for further calculation you can see your previous result, you need dr by dV. So from here you can find the value of dr by dV. Okay, since V is equal to 2n R cube, so you can easily say that dV by dr will be what? This will be 6n R square. 6n R square. And therefore, what will be dr by dV? This will be reciprocal of this. This dr by dV is equal to 1 over 6n R square. Okay? 1 over 6n R square. Now, let us substitute this value of dr by dV when equilibrium will be established in this equation, in the equation number 5. And also we will put the value of V, which is actually equal to 2n R cube. Okay, but in equilibrium you know R is equal to R naught. So where there will be R, you have to put R naught. Okay, so in equilibrium condition, the bulk modulus of elasticity or the reciprocal of the adiabatic compressibility K is given by V, and V will be now written as 2n R naught cube, not R, because system we are considering the system in equilibrium state. So R has been replaced by R naught, and times what? Times dr by dV whole square. But what is your dr by dV? See the equation number 7. This is 1 over 6n R square. So when you will square it, this will be 36n square R4, but R will be replaced by R naught. So this is 36n square R naught. And times, you can see, d2 phi by dr square. d2 phi by dr square. Okay, so this is d2 phi by dr square, but at R equal to R naught. Okay, now let us simplify it. You can see this n and this n will, one of the n will cancel out, and 2 will cancel out. Here there will be 18, and this R naught cube will cancel out, and in denominator there will be only R naught. So B or 1 over K, this is equal to 1 over 18n R naught times d2 phi by dr square at R equal to R naught. This is actually our expression for the bulk modulus of elasticity of the NaCl crystal, or reciprocal of the adiabatic compressibility K for that crystal. Okay. Now we will actually find the value of d2 phi by dr square in equilibrium condition, and for this you have to think some of the previous results. Actually what now I am going to write here, you have already studied in my previous lecture on calculation of binding energy of ionic crystal. So if you have not watched my video on the calculation of binding energy of ionic crystal, you must see that video. You will find there that this phi, which is interaction energy, this is equal to n times phi I. Here phi I is the interaction energy when interaction of an ith particle, ith ion takes place with all other ions. And in the previous lecture, we have obtained the expression for this phi I, and you have seen this phi I is equal to this much. So I have substituted this value here directly because we have already learnt these things in my previous lecture. So instead of this phi I, you must write Bn over r to the power n minus alpha E square over r. Alpha E square over r. Actually here Bn is actually the repulsive constant. And you know alpha is called Madelung constant. All these things you have learnt in the previous lecture. But here, for the calculation of this B or K, we need the value of d2 phi by dr square in equilibrium state. So you must differentiate this phi with respect to r for getting that value. So what will be this d phi by dr? You can see n is at each. And here in the first term inside the square bracket, you have to differentiate 1 over r to the power n. And the dc of 1 over r to the power n is equal to minus n over r to the power n plus 1. So the first term inside the bracket will be minus n times bn divided by r to the power n plus 1. Okay. Now in second term, 1 by r will be differentiated, which is equal to minus 1 by r square, but already minus is present here, so minus minus will become plus. So the second term becomes alpha E square over r square. Okay. So d phi by dr, what is this d phi by dr? This is n times minus n times bn over r to the power n plus 1 plus alpha E square over r square. Okay. But we need the second order derivative. So again, differentiate this result once again. So d phi by dr is equal to this much. Now you can find d2 phi by dr square. And you can see this d2 phi by dr square will be equal to n times n into n plus 1 bn over r to the power n plus 2 and minus 2 alpha E square by r cube. This is a simple differentiation. You can do it. Okay. Now we have to find the value of this d2 phi by dr square at r equal to r naught in equilibrium condition. So for getting this value, you must replace all r in RHS by r naught. So d2 phi by dr square at r equal to r naught, this will be what? This will be n times n into n plus 1 over r naught to the power n plus 2 times. Now here I have directly substituted the value of Bn because you have obtained the value of Bn in your previous lecture in the calculation of binding energy of ionic crystal, and you have seen that we have obtained Bn is equal to alpha E square times r naught to the power n minus 1 divided by n. Okay. This is the value of Bn which we have obtained in my previous lecture. So you must remember it. So here the value of Bn has been substituted and the second term inside this bracket is at each. You can see. Now see here, this n and this n will cancel out, okay? And this r naught to the power n minus 1 will cancel out, and here inside in the denominator there will be r naught cube after cancellation, okay? So our result is d2 phi by dr square at r equal to r naught equal to n times n plus 1 alpha e square over r naught cube minus 2 alpha e square over r naught cube. And you can see we can take this alpha e square over r naught cube as a common factor. So taking this as a common factor, what will be your result? You can see this will be n plus 1 minus 2. And n plus 1 minus 2, this is n minus 1. So finally we get d2 phi by dr square at r equal to r naught. This equals n times alpha e square n minus 1 over r naught cube. Okay. So in this way we have calculated the second order derivative of the interaction energy phi with respect to r when r is equal to r naught, that is our system is in equilibrium. Okay. Now after getting this value, we will substitute this value in the equation number 8. Equation number 8, where we have obtained the value of bulk modulus or the reciprocal of adiabatic compressibility in terms of this derivative. So let us substitute it here. So you can see 1 over k, this will be 1 over 8 n r naught times d2 phi by dr square at r equal to r naught. But see this equation 9, where we have obtained the value of d2 phi by dr square at r equal to r naught, and this is this much. This is n alpha e square n minus 1 by r naught. Now simplified, this n and this n will cancel out, okay? And from here you can see the algebra, n minus 1 will be simply equal to 18 r naught 4 over k times alpha e square. And so you can say that n is equal to 1 plus 18 r naught 4 over k times alpha e square. This is the value of n, that is the repulsive exponent, because you know this n occurs as power on r in the expression of repulsive force or energy due to a repulsive force of the crystal. So this is called repulsive exponent. So in this way we have obtained the expression for the repulsive exponent n in terms of the adiabatic compressibility k of our ionic crystal. If you will take the particular example of sodium chloride crystal, for sodium chloride crystal, the adiabatic compressibility K is equal to 4.26 times 10 to the power minus 12 centimeter square per dime. This is the measured value. And in this case, this this distance r naught, which is actually called critical distance, this is found for NaCl crystal equal to 2.82 into 10 to the power minus 8 cm. So, and we have obtained the value of Madelung constant in our previous lecture. This alpha, you know, this is almost equal to 1.38. So when we will substitute all these values in this expression, and you know E is the electronic charge, this is 1.6 into 10 to the power minus 19 Coulomb. So after substituting all these numerical values in equation A, it is found that this n, which is actually the repulsive exponent of ionic crystal, this comes out almost equal to 8. So n in this case is almost equal to 8. Okay. You can also measure this K. If N is known, then K can be measured. And if N is known, you can measure the range of this short range of this repulsive force also. Okay. So I hope you have definitely understand clearly all the steps of the calculation which I have made here. So go through the video seriously, write down these things in your notebook and revise it. Everything will be crystal clear to you. Okay. Thank you very much.